Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the polymer production process. Those who are well accustomed with the polymer production process, they already know that polymer production process is a combination of various steps. The first step is monomer synthesis and purification, because monomer is the building block of a polymer. Many monomers, they come in combination. Combinedly, they form a polymer. Okay? Either they condense or they form a chain to produce a polymer. And that is called the polymerization. So after it is polymerized, the polymer is separated from the mixture and it is sent for processing. Okay? So that is how the monomer is synthesized, purified, polymerized, and the polymer is separated and sent for processing. So this is the total polymerization production process. Now, in this lecture, we will only discuss the basic information of the polymerization process that is required for the simulation in Aspen Plus. We will not go into the very details of polymerization process because Aspen Polymers is a separate software which is integrated with the Aspen Plus that provides a wide possibility of modeling and simulation on polymerization process that includes the estimation of thermophysical properties, polymerization kinetics, rheological and mechanical properties, polymer molecular structure, and mass and energy balances. So after studying this lecture, if anyone is interested to go to the Aspen Polymer software, they can learn it better. Now let us understand a few classification methods of polymerization reactions. So the classification may be based on growth mechanism, based on reaction conditions, or based on catalyst type. In growth mechanism, there are two types of growth mechanism. One is step growth, another is chain growth. Step growth, it is also called condensation polymerization, and chain growth polymerization is also called as addition polymerization. We will discuss them in detail. First, let us understand the step growth polymerization. Now, step growth polymerization, monomers with functional subgroups react in a stepwise manner. That means when a monomer is attached to another monomer, they react with another monomer and form a dimer. Okay, so that way the entire liquid solution will be full of dimers because every monomer will be reacting with another monomer and form a dimer, right? And then the entire liquid will be full of dimers. Then dimers will start reacting with another dimer and they will produce a trimer. Okay, so that way the monomer will become dimer, dimer will become trimer, trimer will become tetramer, then pentamer, then hexamer. So depending upon the number of monomers get attached, the size of the molecule will increase along with its molecular weight. So both the size and the molecular weight gets increased. So this is also called a condensation polymerization. As if the monomers are getting condensed into dimer, the dimers are getting condensed into trimers, trimers are getting condensed into tetramers, and so on. And in this process, some small byproducts are obtained, such as water or methanol, and they need to be eliminated from the solution. Now in Aspen Plus, we have the segment-based power law reaction model named segment bus. So we have to use this power law kinetics for a step growth polymerization. Now there are several examples of step growth polymerization. One is polyester, that means polyethylene terephthalate or PET. You will get PET bottles, PET plastic bottles. It is commercially available everywhere because soft drinks or mineral waters are sold in PET bottles. Okay, so how this PET is generated? It is by reacting terephthalic acid and ethylene glycol. Okay, so this is a step growth polymerization reaction. Then polyamides. Polyamides, an example is nylon 6,6, and this is produced from hexamethylene diamine and adipic acid. Okay, so this is also an example of step growth polymerization. Then polyurethanes, production of polyurethane also is a step growth polymerization reaction. On the other hand, in chain growth polymerization reaction, which is also called addition polymerization, in this type of polymerization reaction, the monomers with double bonds react through chain mechanism. For instance, if we have a monomer like this, it has some double bond. Now the double bonds are opened and it is connected with a monomer like this. And then this monomer will also have a double bond. This will also get opened, and then we will have another monomer that will connect through it, and we will get a longer chain. So gradually the monomer will keep on adding with this, forming a chain. Okay, so this is a chain formation of monomers. So this is called a chain growth or addition polymerization. Now there are various reactive species such as radicals, cations and anions that propagate the chain. And as you can understand, the addition polymerization is a very fast process as opposed to the condensation polymerization where monomers first form dimers, then dimers will form trimers, and then they will form tetramer, which is stepwise growth mechanism, which is a slower reaction as compared to the chain growth mechanism. So in chain growth mechanism, it is very fast. So high molecular weight polymers form early in the reaction. Now there are several types of addition polymerization. They are free radical polymerization, cationic and anionic polymerization, and coordination polymerization. In Aspen Plus, the free radical polymerizations are given as free rad model or emulsion model. Free rad model is used in the liquid phase reaction, while emulsion model is used in emulsion phase reaction. The examples are polyethylene, polystyrene, PVC, etc. These are the examples of free radical reaction. On the other hand, the cationic and anionic polymerization reactions are given in ionic model. Okay, the example of cationic polymerization is polyisobutylene, and anionic polymerization we will find in polymethyl methacrylate or PMMA or styrene butadiene rubber or SBR. These are the examples of anionic polymerization. And we also have coordination polymerization. This is also a type of chain growth polymerization. Example is isotactic polypropylene, then HDPE, that is high density polyethylene, using Ziegler-Natta catalyst. So it is used with Ziegler-Natt model. So these are the examples of chain growth polymerization. Now those are the classification using growth mechanism. Now this is a classification based on reaction conditions. So there are 4 types of classification: bulk polymerization, solution polymerization, suspension polymerization, and emulsion polymerization. The bulk polymerization, we do not use any solvent. And as there is no solvent, so there is no need for purification. We have high purity polymer in this. But the downside is, it is very difficult to remove the heat. This is the downside of bulk polymerization. On the other hand, we have solution polymerization where we use some solvent, and in a way, the heat dissipation is quite improved, but it requires solvent removal, so purity is the concern. Then we have suspension polymerization, where monomer droplets are suspended in water and forms bead-like polymers. And finally, we have emulsion polymerization, where monomers polymerize within the micelles used for latex dispersion. So these are all based on reaction conditions, and based on the catalyst type, we have Ziegler-Natta polymerization, which uses transition catalysts like TiCl4, AlR3 that produces stereoregular polymers. And metallocene polymerization, it is useful for more precise molecular weight control. And finally, enzyme catalyzed polymerization, it produces biopolymers like polyhydroxyalkanoates or PHA. These are few classification methods of polymers. Now let us understand what are the components that participate in polymerization, because when we add the components in Aspen Plus, we have to identify those components, whether it is a polymer or an oligomer or a segment or a monomer or other conventional components. So based on the identity, its activity will be defined. For example, monomer is a molecule that can be bonded into other identical molecules to form a polymer. Okay, so monomer, as I have already explained in the growth polymerization and chain growth polymerization, how the monomers build a polymer. So monomer is the single building unit. Then small polymer chains containing up to 20 repeating units. So it's small chain polymer. Their special name is oligomer. So oligomer means a small chain polymer. And polymer, by definition, it's a product of polymerization process that typically has large molecules or macromolecules, where a smaller constituting structure is repeated along the chain. It can be a homo or copolymer. Homopolymer means a single monomer is repeated. So this is a homopolymer chain where a repeating monomer is added. That means a single monomer is repeated in a chain to form a polymer. So that is called a homopolymer. Whereas copolymer means there may be two types of monomers. Suppose monomer A is coming twice, and then monomer B is coming thrice. Then again monomer A is coming twice. Then again monomer B is coming thrice, and this combination continues. So it is a polymer chain which consists of two monomers followed by three monomers, and this AABBB forms an unit, and this unit is repeated. In other words, the copolymer is built with two or more monomers. So this is called a copolymer. And finally, we have the segment. Segment is a structural unit of polymer or oligomer and are divided into types depending on their location on the polymer chain. If they are repeating units, then it is called repeat. If they are end groups, now a polymer. Irrespective of the length of its chain, somewhere the chain has to end, right? I mean, the monomer chain cannot go up to infinite length. Somewhere it needs to end. Now, how it will end if monomers are continuously adding with each other? So there must be some ending components or end groups. In most of the cases, the end groups may be hydroxyl group or say methyl group. Okay. So in that case, suppose after some time, a hydroxyl group comes at the end of the chain and the chain becomes dead over there. So the polymer is not live anymore. So this live and dead polymer concept is also there. As long as the polymer chain is in a position to accept new monomers to come and join in its chain, it is called a live polymer or reacting polymer. The moment an end group comes and joins at one end and that end becomes inert, then it is called a dead polymer. That means that polymer chain is no longer capable of increasing its size. Okay, so that is the meaning of the end group. And then branch points. It is not necessary that a polymer chain will only have the reactive sites at the end. The reactive sites can be at its branch also. Suppose this monomer may have a reactive site at its branch, and from that reactive site, another chain of monomers they pick up. So it becomes a branching. So this may be a branch, this may be a branch, and so on. So these branching points also can be defined by the segment. Okay, and there are other conventional components such as the initiator, co-initiator, catalyst, solvent. Initiator means in a polymerization reaction, some component has to initiate the reaction because monomers, otherwise it is a stable component. For instance, styrene, otherwise it is a stable component. But the moment some initiator initiates a reaction, the polymerization begins. So initiator, co-initiator, catalyst, some catalyst may make the reaction faster. Okay, so and solvent. So these are the extra conventional components that may be added into the polymerization reaction. Then we have a segment type. Just now we discussed about the segment over here, structural units of a polymer. So we can further discuss about the segment types. Oligomers do not require component attributes. For an oligomer, we should specify the number and type of segments that it contains. Repeat, we have already discussed core repeating units of the backbone or branches, that is polyethylene, polystyrene. For instance, in polystyrene, the styrene is repeated at the end and forms a chain. So it is a polystyrene. The end group, that means the terminal units capping the polymer chain. I have already discussed about this. Hydroxyl group and methyl group, when it comes at the end of the chain, then the chain ends there. It is a termination of the polymer reaction. And then branch 3, branch 4. Branch 3 means tertiary branches extending from main chain or primary branches. For instance, the low density polyethylene or LDPE, that is an example of branch 3 segment. And branch 4, that is quaternary branches extending from branch 3 segments, used for highly branched polymers, example dendrimers or hyper branched polymers. Okay, so these are the several types of segments that we can identify. Then we will come across the polymer component attributes. Properties such as molecular weight and composition, it varies throughout the flow sheet with time because polymerization reaction is time dependent. As we progress with time, the polymer chain length increases along with its molecular weight. When a component is specified as a polymer, it has associated attributes used to store information on the molecular structure, distribution, product properties, and these polymer attributes enable tracking different properties of live and dead polymers. We have already discussed what a live and dead polymer is. So these are the attributes we will come across, that is weight average degree of polymerization and molecular weight, segment fraction, segment flow, number of long and short chain branches, long and short chain branching frequencies, number and frequency of crosslinks, number average block lengths, that is sequence length, and flow and fraction of terminal bonds. Terminal bonds means where the polymer reaction ends, the chain ends. Now, with this small recapitulation of polymerization theory, we will directly go into the example because until unless we see it in the Aspen Plus window, we will not learn it fully. So we will take this small example and then we'll solve it in Aspen Plus, and while solving, we will understand it better with much more insights to them. So the problem is a feed of 5000 kg containing styrene monomer. So feed contains styrene monomer. The feed temperature and pressure has been given, is the subject of polymerization. That means styrene will produce polystyrene, right? In a series of 3 CSTRs with volume 15 meter cube. Okay, so there are 3 identical CSTRs with a volume 15 meter cube. The reactor feed contains 98% of styrene, so 5000 kg out of which 98%, that means 4900 kg per hour is styrene. Rest are 1.9 weight percent ethyl benzene, 0.07 weight percent of N-dodecyl mercaptan. In short form, it is written DDM, acting as chain transfer agent. So both ethyl benzene and DDM, they act as chain transfer agent. And 0.03% of di-T-butyl peroxide or TBP as initiator. Already I have told initiator initiates the reaction. It decomposes and then it shoots the reaction from that point. Styrene should also be considered as a repeat type segment. Just now we have discussed segment. It can be repeat, end, branch 3, branch 4. In the previous slide we see. So styrene should also be considered as a repeat type agent and as a co-initiator too. So not only TBP is an initiator and styrene also is a co-initiator. Then we have unreacted styrene containing some ethyl benzene, TBP and DDM is flushed and separated from polymer. So basically we have 3 reactors in series, and after that there is a flash, and this flash operates at 220 degrees centigrade. Polymer is separated and unreacted styrene containing all these things, they are sent for cooling and mixing with makeup stream. So this is cooled somewhere and then they are mixed with a makeup stream and returned to the first reactor. So here it will be recycled, as some of the portion of the reactants, they form polymer and they are taken out. So a makeup stream with that amount of styrene which has been produced at polystyrene, so that amount will be fed back into the system. So this is the makeup stream. All reactors work in liquid phase only. The temperature is 120, 160, 200 degrees centigrade in the first, second and third reactor respectively. That means although all the reactors are identical, that means they are of size 15 meter cube, but still their temperature is different. First reactor works at 120 degrees centigrade, second reactor works at 160 degrees centigrade and third reactor works at 200 degrees centigrade. The entire process operates at 1 bar. So the entire process operates at 1 bar. Use poly-NRTL property method. So property method has been specified. Di-T-butyl peroxide. It is a pure component with molecular weight. It has been given. Use free radical kinetic model with kinetic constants available as follows. That means, as you may remember that while discussing the reactions, we remember polystyrene, this is a free radical polymerization reaction. So here it is said use free radical kinetic model. As it is a styrene polymerization reaction, So we have to use free radical kinetic model. Now the kinetic constants are available as follows. This is the equation, free radical rate constant equation. Now these are the set of reactions. That is, the first reaction is initiator decomposition. TBP is the initiator, so it dissociates or decomposes. Then there is thermal induced initiation, chain propagation, chain transfer to monomer, chain transfer to ethyl benzene, chain transfer to DDM, chain termination by combination. All those things are there. Assume quasi-state approximation and special initiation reaction with thermal initiation coefficients of 3 for styrene. This we will understand when we go to the Aspen Plus software. Now, continuing the example, we have to vary the temperature of second reactor between 120 degrees centigrade and 180 degrees centigrade with an increment of 5 degrees centigrade, and we have to calculate the conversion, polydispersity index, weight averaged molecular weight, and number averaged molecular weight at the outlet of each reactor. So this is the task that we have to perform. Now let us go to the Aspen Plus simulation window and start solving the problem. And in the way of solving problem, we can come across various things that we will learn as and when the things appear before us.